Hello, this is Curtis Jennings and Gabriel Barahona's Engi 460 project part 10, where we will be discussing our conference paper and how we implemented our ideas into an MAS model. Within our presentation, we want to look at our literature view that we wrote in our conference paper, and we want to look at the similarities and the differences between the existing models of literature and our ideas that we want to implement into an MAS model. And then we're going to look at the methodology, the MAS rules, and the justification for an MAS model and why we want to implement it. And the simulation and execution, and we want to look at the architecture and the results that we got from the simulation. Within our research, we came across the first article that used RFID chips for communication of robots. Essentially, the robots, in order to communicate, they were able to read information off other robots' RFID chips. However, for our model, we do not want to use this idea because RFID chips need to send information back and forth from a central main host computer. The second article utilizes a single robot to move around an unknown location of obstacles on the ocean floor. This model, the robot knows where the end location, where the object is, where it's trying to find. However, it does not know where the obstacles are, and we want to use this idea that the robots in our model do not know where the obstacles are located. And our model, the robots also do not know where the spills are located. The third model uses ethanol as a substitution for the pheromone. And this is an important literature piece of literature because it looks at the pheromone and how that is related to the communication of the agents. The main similarities between the existing models in literature and our model is that they both use the concept of pheromone, and they both need to detect obstacles that are located within the simulation. But the main differences that make our model unique is that we want to use independent communication of the robots. We want to use the sensors to be able to intercommunicate between the robots and understand where the spills are located based off of the paths that have been taken by the robots, and also where the home base is once the robots have detected the spill. And we want to use multiple agents for the simulation.
Okay, so now we're going to talk about the MAS rules for chemical hazard detection. And basically there are three major rules, and the first rule is the hazard spill entity selection rule. And this rule defines that once several spills have been detected, the robotic system applies the use of the greedy neighbor algorithm, in which the shortest route back to the home node will be dynamically selected throughout time. And this shortest route selection will be physically possible due to the pheromone-like mechanism that is stronger in shorter distances, allowing the system to select this higher gradient paths. The second major rule is the sound emitting and sensor detection rules. And this sound sensors would replace a pheromone already in the Mason foundational model of the ants foraging. And the sound detection will be used since the robot will assist other robots nearby to the location of the apparent chemical spill or hazard, and once the robot detects a spill, it will begin this beeping at a specific frequency, which will attract the other robots to randomly search within the area where the sound is coming from. Besides this, there will also be an independent sensor in the home location which will be beeping at a different frequency, and this will only be triggered once this frequency would only be triggered to be heard by the other robots once one of the robots has detected the actual spill. The third and very important MAS rule is the self-assembly cleaning rule. And this rule basically defines a collaborative self-assembly of robots, and once a chemical spill has been detected, unlike the ants foraging model, this model will detect and eradicate any hazard, and will specifically detect how many robots are needed. If the spill is too big, more robots will arrive. If a spill is too small, not as many robots will arrive. And this leads to the justification of why we need a multi-agent simulation model for a chemical spill detection in a manufacturing environment. And first of all, allowing multiple robots in a manufacturing facility to be simulated at one time will allow spills to be detected faster, and there will be no hassle of waiting for one cleaning machine or robot or whatever, or whichever mechanism is used to clean spills, to randomly or search throughout the entire facility, instead of having multiple agents that will do this at a faster time. And this arises a sub-optimization problem in which the robots are meant to be attracted to the sensors of multiple robots around them, and as I mentioned, find the shortest route back home. Okay, and now the simulation and execution environment. First of all, the simulation architecture of this MAS model consists of three major parts. The first part is the actual robot code, and this code deals with the local behavior of each independent robotic entity, and it provides the algorithmic code with a Boolean variable when, if a robot detects a spill, it will apply the greedy neighbor algorithm to pick the shortest route back home. The second one is a robot interaction, and this allows robots to interact with both the home location and the spill locations, as well as with the different obstacles, which are the different circles that represent workstations in this whole manufacturing facility. And the third one is the robot interaction with UIN. This is just the 2D portrayal of the visualization of our code, and it defines and initializes the dimension space along with attaching the display portrayals and the color visualization, such as the blue for the path and the green for the pheromone, and the colors for the obstacles as well. And once we have discussed our simulation architecture, we're going to talk about our execution. As you can see, both of the figures below demonstrate the results of our execution. So first of all, there are 8 circles which represent different workstations. The middle circles represent the main workstation, and this is a job shop manufacturing facility where there are different workstations that feed to the middle workstation, which is a main assembly line, manufacturing line. And the spills are located near these workstations because most likely in a manufacturing environment, any spill or any chemical detection will be located near the areas where people will be working on it. Workers will be working with chemicals, working with any industrial products. So it is more likely for there to be spills around these areas. And as we can see, there are 2 paths. So the robots have detected both of the spills, and in the end they have cleaned one of the spills and returned to the other spill, and they have finally stayed on the higher gradient, which is the spill with the shortest distance from the home.
So in conclusion, there are many benefits of using an MAS model for simulation and implementation of our ideas. We want to replace centralized units or manual labor. So automation was the big idea that would improve processes of cleaning up spills within a manufacturing facility. So it really is an improvement of industrial hygiene in highly industrial environments, and automation of self-organizing robots are able to detect spills through independent communication. That was our idea, and we think that it is feasible to implement into an actual manufacturing facility, and that our MAS model is able to demonstrate that. This is our works cited and the articles that we use for our literature review within our conference paper.